Today we are going to discuss the fully controllable or fully controlled devices. As I said before, this is going to be the last chance we discuss about power semiconductor devices before we enter into discussion about every power converter, every kind of power converter. Because we don't want to spend too much time here in the beginning when you really don't have a very good understanding of how power converters are working. So we're going to discuss only in this class, and after we have completed discussion about all different types of power converters, we'll come back. We'll come back and spend a little more time on the new technologies in the power semiconductor devices area. And at that time, I hope you will have better understanding of what's going on in the power semiconductor devices. So today we are going to complete discussion about fully controlled devices. I listed 4 different devices here. Gate turn-off thyristors, that's GTO. Giant transistors, GTR. Okay. And there's another one, it's very long name, but in short we call that power MOSFET. And there's another one, the 4th one is called IGBT. These are all devices, typical devices that we can turn it on and turn it off through control terminals. So that's why we call that controllable, fully controllable or fully controlled devices. And there are common features we will see in the later discussion. They are all employing IC fabrication technology as integrated circuit. They all employ IC fabrication technology. We'll see in a later discussion about that. And they are all fully controllable, and they're all used in high frequency, higher than the half-controlled devices. Switching frequency is higher than thyristor. And applications is very wide. They began to be used in large amount in 1980s. If you still remember when we discussed about the history of power electronics, we mentioned that the history of power electronics is always developing, always evolving with the development of new devices. Okay. So when thyristor was invented, it opened a new era for power electronics history. And when these fully controllable devices were invented and applied to practical applications, they actually started a new era of the power electronic history. And that era was started in 1980s. But right now, talking about these 4 different types of fully controlled devices, I would say the first 2, GTO and GTR, those 2 devices are seldom used today. They became obsolete. Okay. obsolete. Okay, and IGBT and power MOSFET, these are the two types of devices that we mainly use today. So they are the two major power semiconductor devices nowadays. Okay, so our focus will be on the introduction of power MOSFET and IGBT. But before we get into that focus, we still want to talk a little bit about the first two. We still want to talk a little bit about GTO and GTR because we have to know some basics. Let's see. GTO, gate turn-off thyristor, actually we can imagine from this name that this is basically a development from thyristor. And the ordinary thyristor cannot be turned off through control terminal, through the gate, but this type of thyristor can be turned off through gate. So this is called gate turn-off thyristor. Of course, it has a Chinese name. But this is very long, so usually we, even in Chinese, we call the short name GTO. You can see the basic structure is similar to thyristor. This is still four-layer devices. 1, 2, 3, 4. Four-layer devices. Okay, just like thyristor. But in order to make this thyristor to be able to be turned off through the gate, there must be some differences. There must be some differences in the structure. There must be some differences in the manufacturing or fabrication process. This is always true. The difference in the performance always originates from the difference in the structure. Do you agree with me? This is always, not just for this one, it is for everything. When you have outside performance difference, then the inside structure must have some differences in the inside. Okay? This is always true. Let's look at GTO. What makes GTO so different from ordinary thyristor? Okay, there are several differences. Okay. First one, the gate and cathode structures are highly integrated. Or I would say more exactly, it should be this structure is highly interleaved multi-cell structure. This is different from thyristor. Interleaved multi-cell. This is a multi-cell structure. That means in each GTO semiconductor chip, I have many. You can see from this picture here, this is the picture when you look at the GTO device from the top. It has many small cells, okay, inside each GTO device. And each of these cells has the same structure, same 4-layer structure. Each of the cells is looking like this. Okay, 4-layer, 1, 2, 3, 4, 4-layer device, 4-layer structure. And you can consider, let's see, you can consider this is one cell. Okay, you have a gate, G means gate, cathode, and anode. Okay, and this is this. You can consider this as a second cell. Okay, many cells, many small cells of small GTOs. So this is what we call interleaved. What is called interleaved? Because the gate and cathode, they are manufactured at the same site, but they are placed in an interleaved manner. You have gate, cathode, gate, cathode, gate, cathode. That's called interleaved. So this is one of the major differences between GTO and ordinary thyristor. The reason we are doing this, of course, is trying to make this thyristor being able to be turned off. Okay? So that's the major reason. Okay? In order to have the ability to be turned off through gate, you have to have this. And actually, we didn't mention this in the Chinese textbook. There's another reason. Another reason for this is to avoid current crowding. When you manufacture the GTO in such a way, with this multi-cell structure, this can help to avoid current crowding. What is current crowding? Current crowding means when this thyristor starts to be conducting current, it tends to be conducting from the center part. Okay? All the current tends to be concentrated in the center part and then gradually enlarged, expanded to the whole area of the cross section, the whole area of GTO. If this process is too long, if the whole current is concentrated in the center part for too long time, then this might be very harmful to the device, because in the center part of a very small area, you have such a large current, this may destroy the device. And this structure, multi-cell structure, helps to distribute the total current evenly in the whole area, in a larger area, and avoid current crowding. That is very good for the device. Okay, so that's the first difference. There are other differences. Okay, I will mention in the next slide. The other difference is usually when we manufacture this thyristor, we intentionally make. Let's see, there is one. We intentionally make the coefficient intentionally control the coefficient of these two transistors. Remember the two transistor model we mentioned in last time when we discussed the operation principle of thyristor. A thyristor can be considered as the connection of two transistors. We intentionally make the coefficient alpha 1 and alpha 2. This is very carefully controlled. We make sure these two coefficients are specifically controlled. Okay? So that when the thyristor is turned on, these two transistors are not in a very deep saturation area, not deep saturation. Not very deep saturation area. And therefore, when we turn it off, it is easier to drag these two transistors back, okay, from the saturation state back to the cutoff state. Okay? In general, this process is very complicated. Although we had some discussion in the textbook, but actually this process is very complicated, and even with the control, the selection of alpha 1, alpha 2, very complicated. Okay? But we don't need to get into that deep. We just understand we have very special control when we manufacture the DTO, so that alpha 1, alpha 2 are very carefully controlled and make it easier for us to turn it off. Okay? There are other differences here. There's a short difference. The distance from gate to cathode is very short because gate and cathode are laid out side by side. This is called interleaved. Therefore, this distance is very short, so that we make it possible to drive current out of gate. Okay? Remember last time we mentioned for ordinary thyristor, if you want to turn it off, the only way is to make sure the current flowing through thyristor to be decreasing to nearly zero. But we also mentioned there's another possibility. If we can inject a reverse current from the gate, that is another possibility. Inject reverse current from the gate, that may turn off thyristor. That's the operation principle of GTO. We are trying to inject a reverse current from the gate to turn off GTO. And in order to realize that, in the inner structure we have so much differences. First, we have this interleaved multi-cell structure. Second, we have this intentionally selected coefficient alpha 1 and alpha 2 for these two transistors. Okay? And this arrangement makes sure we have the ability to turn the GTO off through a gate terminal. So I don't want to spend too much time here. Just want you to have a feeling, have some basics of GTO. What makes GTO controllable, fully controllable? We have differences in the inner structure. There is a discussion in the textbook about static characteristics. Okay, this is almost identical to conventional thyristor in the forward direction. There is also discussion about the switching characteristics of GTO. This is different from thyristor. You can see the turning on process is probably the same. We need to, the upper waveform the upper waveform is the gate, the current you inject into the gate. So when you turn on a GTO, you inject positive current into the gate. And therefore, the turning on process, turning on transient is here. You need some time for the current to be gradually start to increase. So there is a delay time. This is called turn on delay time. After some time, the current flowing through the thyristor starts to increase. This is called current rising time. Okay. So when the current has reached the steady state level, you actually don't have to inject current into the gate anymore. The thyristor will kept under the on state by itself. So this is called trigger. You can actually, after this point, you can take out the gate current. The thyristor will still be in conducting. So there will be current conducting. Okay? That's the turning on process. The turning off process is like this. You need to inject a reverse current into the gate. You inject reverse current into the gate. And then it takes some time for the current starts to be decreasing. This is called turn off delay time. You need some time for the current to be starting to decrease. And then for the current to decrease from steady state value down to be nearly zero, that's called current decreasing or current falling time. Okay? Because that's the switching characteristics of GTO. Of course, we have some specifications of GTO. Most of the specifications of GTO have the same meaning, same definitions as those of thyristors. Most of them are the same definition. But there are different, of course, different specifications. For example, the maximum controllable anode current. Maximum controllable anode current. That is actually referring to the maximum current you can turn off through the gate. Okay, you can turn it off. Okay. Okay, there are other discussions about current turn-off gain. Okay, that means the ratio between the current you are going to turn off and the gate current the reverse gate current you have to inject into the gate. Okay? And there is another specification about turn on time, turn off time. We have already discussed about that. Okay? That's GTO. GTO was quite widely used in 1980s and even in 1990s. But later on, much better devices appeared. That is IGBT. IGBT is much better than GTO in almost all every aspects. In almost every aspects, IGBT is much better than GTO. So currently, GTO is almost no longer used. There are still probably some GTO used in some old equipments. GTOs are still used in some old equipments, like in elevator, motor driving. But if you talk about manufacturing new equipment, people no longer use GTO because IGBT really are much better than GTO in almost every aspect. GTR, we also want to spend a little time on GTR. GTR, this name is actually the short name for giant transistor. Giant. It is actually the same or similar to the transistor we learned before in the information electronics. The only difference is that giant transistor, GTR, can handle very high voltage and very large current. That's the only difference. Okay? So you can see the first statement, GTR is actually the bipolar junction transistor. Bipolar junction transistor. That can handle high voltage and large currents. And therefore, sometimes GTR is also called bipolar junction. Bipolar, we take the first character, junction, transistor. So sometimes it's also called power BJT. Power BJT. That means it can handle high voltage, high current. This BJT can handle that. Or just BJT. Okay? The inner structure is similar to the ordinary transistor, the transistor we learned in analog electronics. It is NPN. You have N layer, this P layer, NPN, or PNP. Okay, 3 layer. Of course, you may have noticed the difference. This is not exactly 3 layer. There is an extra layer inside, in the middle. This is the N- layer. N- layer. Now what's the? You can imagine what's the function of this N- layer. You don't remember? How do we handle high voltage? For diode, for power diode, how do we handle, how can we have the ability to block high voltage? That's this N- layer. N- means the doping, the carrier density is very small, very low. Very low, and therefore this layer is similar to intrinsic semiconductor. Therefore, it is able to deal with high voltage. So that's the similar thing. Similar things here. Similar to diode, power diode. Remember, for power diode, there is PIN structure. It's not just ordinary PN junction. There is a third layer. I means intrinsic. That means you insert N minus layer for power diode. Here, we insert this N minus layer to handle high voltage too. Do you still remember that? Yes or no? Not too many students are nodding their heads. Okay? So when you learn the device, as I mentioned, the difference in the performance always originates from the difference in the structure. Okay? I said power transistor or giant transistor, GTR, the inner structure is similar to the ordinary transistor in information electronics. The only difference in the performance, the only difference is that giant transistor can deal with very high voltage and very large current. Then there must be some differences in the structure of GTR, different from ordinary transistors in information electronics. Okay? The structure that makes GTR be able to handle high voltage is this N minus layer, extra N minus layer. For ordinary transistor in information electronics, they don't have this. This can block very high voltage. Okay? In order to deal with large current, do you still remember for power diode, what are the features that make power diode be able to handle large current? Do you still remember that? Larger size, somebody said, right. It has larger size, okay, of course. Larger size make it possible to handle large current. What else? Not sure, still remember that. Vertical structure. This is a vertical. Okay. For information electronics, everything is flowing on the surface, flowing. The current flow direction is parallel to the surface. I draw a picture here. Okay. If you have a, let's see, this is, let's see, this is the P, this is N, P, N. For the ordinary diode, so that the current is actually flowing in this direction. That is parallel to the, you put a, this is, let's see, this is anode terminal, and this is cathode terminal. So when you apply voltage between A and K, the current is flowing along the surface, parallel. That's parallel. But for power diode, this is a vertical structure. They put K in this side. The current is flowing in vertical direction, vertical to the chip surface. That makes the current flowing cross-section area much larger than the ordinary diodes in information electronics. Okay? So these are the two things that make power devices, power diode, to be able to handle large current. Similar here for GTR. GTR has larger size than ordinary transistor in information electronics. It has vertical structure. You see, this is a vertical. This side is collector, and that side you have emitter and base. This is a vertical. The current flowing is vertical direction. Okay? So these are the two things that make GTR different from ordinary transistor and make it being able to handle large current. Okay, there are other structures, other differences mentioned in the textbook. For example, it has Darlington structure. Darlington structure. Okay, this is Darlington structure. You have two transistors connected in this way, and the first transistor emitter current is actually providing the base current for the next transistor. That makes the amplifying coefficient very larger than just one transistor. This also helps the GTR to be able to handle large current. Okay, similar to GTO, this structure is also interleaved multi-cell structure, as I mentioned before. This is used to handle, to avoid current crowding. Okay. I will not get into details. The operation principle is exactly the same. Same as the ordinary transistor in information electronics. Okay. And even the symbol, electric symbol is the same. We use the same symbol for GTR, same as the symbol for ordinary transistor. Okay. Did I forget to mention the symbol for GTO? Yes. The symbol for GTO is actually a little different. Different from thyristor, the only difference is here. It has a short line here, this one, across the gate. That means this is a GTO. When you have a short line there across the gate, that means this is a GTO, not ordinary thyristor. Okay? For GTR, static characteristic, same as the ordinary GTR. I believe you have learned this before. The IV curve, static characteristics, can be classified into three areas. Okay? The area when you have very low current, almost no current flowing through, that's called cutoff region. That's called cutoff region. Okay, that's first area. The area when you have very low voltage, and the current could be as high as possible, that is called saturation region. Okay? The area between these two regions, this very large area, this is called amplifying region. Okay? Another name is, sometimes it's also called active region. Okay, so that's all the same as ordinary transistors in information electronics. I believe you have learned this before in analog electronics. Okay. There is a discussion in the textbook about the switching characteristics also, about GTR. There's one difference if you look at this picture here. The upper side waveform is base current. The current you are injecting into the base terminal of a GTR. The lower side is the current flowing through the collector terminal. Okay. If you look at this, you can see if you want to turn on GTR, you are injecting positive current into the base. If you want to turn it off, you are injecting negative current. Inject negative current, or actually, if you understand the basic operations of transistor, actually you just apply no current. When you don't apply current, then this will be turned off. But in order to, in the practical application, in order to make sure the transistor is quickly turned off, usually we inject negative current. This is the switching characteristics. If you look at this, can you notice what's the difference between these characteristics and the switching characteristics of GTO? What's the difference? Comparing this one with the waveform for GTO, what's the difference? Yes, please.
The PS of GTR is longer than GTO.
TS, the storage time. Storage time is also called turn off delay time, storage time. Is longer than GTO? Okay. Are you sure? Not so sure. Well, I cannot see. From these two pictures, this picture and the picture about GTO, I cannot see this is longer or not, because I didn't label the exact numbers of time. Any other students? Let me see. Pay attention to the base current and the gate current of GTO. Base current of GTR and base current of GTR and gate current of GTO. What's the difference? Yes, please.
Can you also inject a consistent IB to keep the GTR on?
Okay, good. If you look at this picture here, for GTO, if you want to turn it off, we inject gate current, and that gate current does not have to be always there. Once GTO is turned on, you can remove that gate current. That's what we call triggering. Okay? But if you look at the GTR, if you want to turn GTR on, you have to always put certain base current there. You have to always inject base current to make sure GTR is turned on. That's the difference. That's called level controlled or level sensitive. Sensitive. So for GTO, this control is triggering, but for GTR, this is level control. If you want to make it on, you have to always put control signal there. And that also brings the difference in turning off. Okay? If you want to turn off GTO, you have to inject reverse current. And once GTO is turned off, you don't have to inject reverse current anymore. Okay? And then ideally, theoretically, for GTR, if you want to turn it off, actually you don't have to inject reverse current. You just remove the base current or decrease the base current to 0. Then this GTR will be turned off. When you don't have base current, then GTR will be turned off. The reason we are still inject reverse current is to make sure, in the practical application, in order to make sure the GTR is quickly turned off, we inject reverse current. Theoretically, you don't have to. Once you remove the base current, then the GTR will be turned off. Okay? I want you to make sure. I want to pay attention to this difference. One, GTO is triggering, we'll control that. But for GTR, this is level control or level sensitive. You will notice this difference in the future for other devices. Okay, there's another discussion in the textbook about second breakdown. About GTR. I will not get into details because GTR is obsolete, as I mentioned, obsolete. We no longer use that. IGBT is much better than GTR. Okay, so we don't get into details, but you can read through the textbook after the class. So the safe operating area. The safe operating area for GTR would be defined by the maximum voltage it can handle and maximum current it can allow, and also secondary breakdown boundary and maximum power boundary. These 4 lines form the safe operating area for GTR. Okay? So that's all I want to say about power MOSFET. GTR. Now let's get into the two major ones. Power MOSFET and GTR, IGBT. That's too long. This reading is too long. Let's get a start. Okay. power MOSFET, the full name is power MOSFET. I believe you have learned this before in analog devices. This is the same. MOSFET. Actually, FET means field effect transistor. Field effect transistor. Field effect transistor. And MOSFET is actually a very special type of FET. MOS means metal oxide semiconductor. Metal oxide semiconductor. Metal oxide. Metal oxide field effect transistor. That's MOSFET, the short name, the full name for MOSFET. It is exactly the same in the power MOSFET. It is just a MOSFET that can handle high voltage and large current. Okay? Let's take a break.